Hi folks, today we're going to do a little bit of review from the lessons that we've covered in this chapter so far. So make sure you have your green note card handy and we'll go ahead and get started. First up says about 30% of young American adults ages 19 to 29 don't have health insurance. Suppose you take a random sample of 10 American adults in this age group. What is the probability that at least one of them doesn't have health insurance? Okay, so right now we have two potential outcomes. Either they don't have health insurance or they do. Okay, but these outcomes aren't equally likely. Notice it says 30% chance of not having health insurance, which implies that there's a 70% chance that they do. Okay. Now, we want to look at the probability that at least one of them doesn't have health insurance. Now, if we think about at least one, that means one or more out of the 10. Okay, so this could look like exactly 1, exactly 2, exactly 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's a lot of outcomes to try to think about and probabilities to work with. This situation is actually easier to think about the complement. Okay, we know that complements add up to the entire sample space, but their probabilities also add up to 1. It's talking about the probability that at least one of them doesn't have health insurance. If we find the complement of that, we can just subtract it from 1 to get the answer to this question. Okay, so let's talk about the complement. It says, what is the probability that at least one doesn't have health insurance? Well, that means everyone except all of them having health insurance. Okay, so the complement here Okay, so think about that. Okay, if we want one or more to not have health insurance, if I take out the situation where they all have health insurance, am I getting to this at least one? Okay, hopefully you can see that that works. So let's talk about the probability that this actually happens. Okay, so all have health insurance would mean all 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 have health insurance. We decided that the probability of having health insurance was 70%. That looks like 0.7. Okay, well the second person doesn't care if the first person had health insurance or not. Okay, so these are independent from one another. So we can say 0.7 all the way through here. Okay, well we're not going to do this 0.7 times 0.7 times 0.7 all the way through. We know we can generalize that as 0.7 10 times or 0.7 to the 10th. Okay, so if I go type this in 0.7 to the 10th power, okay, we get this really small decimal here. Okay, but remember, this is the probability that all have health insurance, when we really want that at least one of them doesn't. Okay, so one may not have health insurance, but there could be 2 or 4 or 9. Okay, we don't really know. So all we have to do now is take 1 minus this. Okay, so 1 minus the probability of that to get our final answer. And I'm just going to write it as 1 minus 0.7 to the 10th instead of that ugly decimal. Okay. Again, if you can change it to a fraction, you want to, but in the cases of some of these weird decimals, that's not going to happen with our calculator, and that's okay. So we'll just round it to 4 decimal places. Okay, so the probability of one or more is going to be about 0.9718. Okay. And really, that's the hardest one, in my opinion, on this to think about, just because it saves us time from having to take all those separate, well, what's the probability of 1 happening, or 2 happening, or 3 happening, and adding them all together. Because remember, the total number of outcomes here, if there are 2 options for each person, and there are 10 total repeats, or 10 total people, there would end up being 1,024 different outcomes that we would have to think about here, and that would take forever to try to calculate the probability that way. All right, let's look at another one. It says find the probability of getting a sum of 7 or a sum of 8 when you roll 2 dice. Okay, so remember this word or means add. Okay, if there's an overlap, we'll have to subtract off the ones we count twice, but in general, we add here, okay, and we're rolling 2 dice. So remember for this one, with 2 dice, we've got 6 outcomes, and we're repeating twice, so there's 36 total options, but we're only going to list the ones that help us, okay, but that 36 is useful to calculate this probability. So I like to set this up 1, 2, 3, 4, 5, 6 to talk about my first roll. Sorry, my 5's not working there. And then just think of what gets me to a 7 or an 8. So I'm going to list all of them. That way I don't have to worry about adding them up. I can just look at all of them together. Okay, so 1 I can put with a 6 to get a 7, but I can't put it with anything to get an 8. Okay, 2 I can put it with a 5 to get a 7, or a 6 to get an 8. 3 I can put with a 4 or a 5, and hopefully you see what pattern is happening. Okay, so I can do a 3 or a 4 for the next one, and then I can do a 2 or a 3 for the next one, and finally 6 can go with a 1, or 6 can go with a 2. Okay, that gets all my possible outcomes here. So I just want the probability of that over 36. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 36 cannot reduce. So that is my final answer. Alright. When we're looking at simple probabilities like this, you just add them up. See what outcomes work, put it over the total. Okay. Alright. Next one. At Hayes High School, 80% of the students carry a backpack or a wallet. 40% carry a backpack, 50% carry a wallet. If a student is selected at random, find the probability that a student carries both a backpack and a wallet. Okay, so notice I see this or, which usually implies union, and then I see this both, which usually implies intersection. Okay, this tells me that this may be a good problem to either use one of your formulas on your note card for, or draw a Venn diagram. Okay, I prefer to use a Venn diagram for visual purposes, but you're welcome to use the formula as well. Okay, so our 2 things we're talking about here are backpack and wallet. Okay, now because we know it says 40% carry a backpack and 50% carry a wallet, notice 40 and 50 together is 90. It says 80% carry a backpack or a wallet. 90 goes over 80, and that's what's implying that these actually overlap here before we even got to this sentence where it says find that they probability that they carry both. Remember, the probability that they carry both could end up being 0. Okay, so that doesn't indicate there necessarily has to be an intersection, but that is what we're looking for here. Okay, so let's set it up. We've got the backpack, we've got the wallet, and they're going to overlap. Alright, says that together we're supposed to get up to 80%. Okay, so when we add this piece, and this piece together, we should get 80. Okay, but then it says that 40% carry a backpack. Okay, so that means in this little section of the left circle all the way through, that's 40. And wallet gets to be 50%. Okay, but again, if I take 50 plus 40, I go over that 80%. That's because this middle ground that we're trying to solve for gets counted twice. Okay, so what we're saying is 50% plus 40% minus this thing we count off twice should equal 80%. And that's actually what your note card says. If you take a look at that, okay, it says that the probability of A plus the probability of B minus anything you count twice, the intersection, okay, should be equal, because on your note card it's over here, should be equal to the union. Okay, but it's just as okay for us to put it on this side with that 80%. Okay, union is together, the total, the or. So all we have to do is solve. It says 90% minus x equals 80%. Okay, and that's obvious to see. Our overlap here has to be 10%. Okay, so the probability of both, or the probability here of backpack and wallet, is equal to 10%. Alright. Number 4 is a similar problem with different questions. What I want you to do is take this time right now to pause the video and see if you can draw a Venn diagram for this so that we can answer those 3 questions. Okay. Alright, here's our picture with the given information. 80% swim, but 55% of that are people who can also whistle. So we want to look and try to figure out how many people can only swim. They can't whistle too. Okay, so all we have to do is take out that overlap. So 80 minus 55%, 25%. Okay, then over here, same idea. We're taking 70 minus that overlap of 55%, 15%. Okay, so now let's answer some questions. It says, what percentage of people can swim or whistle? Okay, 2 ways to do this. Okay, you can look at your picture. Swim or whistle means they can do one or the other, or they can do both. Okay, or means add those things all up. Now remember, or suggests that if they overlap, you don't want to count it twice. So that's why your formula says take all the people who can swim, add all the people who can whistle, and take off the intersection. Okay, the separate circles already have that intersection taken off. So 2 options. You can take your 80 plus 70 minus 55, or since we set up our Venn diagram like that, okay, we could take just our 25 plus our 55 and then plus 15. Okay, doesn't matter to me how you get that answer. I'm going to move it down here where I've got just a little bit more space. But we're finding the percentage of people who can swim or whistle. Okay, so for us, let's use our correct symbols here so we can get an idea of what this is meaning. Okay, swim or whistle is the union. Okay, and we just have to go actually add those up. Okay, so 95% of people can do one or the other. Okay, doesn't mean they can do both. Okay, we know that is 55%. So now, on part B, we're asked what percentage of people who can only whistle. Okay, so only whistle is all the people who can whistle minus the overlap. Okay, we did that already to get the 15%. Okay, and percentage who cannot swim or whistle. Okay, we just decided that people who could swim or whistle was 95. Cannot is the complement of that, so everybody else. Everybody else is 5%. Okay, I like to just think of this as 1 minus the union here, because this is not really the same as the union of both the complements together, because again there's overlap there. Alright, next up, Jack and Jill have finished conducting taste tests with 100 adults from their neighborhood. The results are displayed below. It says, I identified tap water correctly in the taste test. B drinks bottled water. Determine mathematically events A and B are independent or dependent. Okay, so let's first read our table here. Okay, so drinks water, bottled water, there's a yes and there's a no. Okay, so the total people who drink bottled water is 30. The total who drink or don't drink bottled water is 70 for the 100. Okay, similarly, identified tap water. Okay, the yes was 24. And the no was 36 out of those first people. And then over here, the no's for identifying tap water, 6 for those drinking bottled water, and 34 for not. Okay, 60-40 making 100. Over here, 37 making 100. Okay, so we want to know A and B. Okay, so we need to look at all the people who identified tap water correctly. Remember to do an independent test. We need the probability of A, probability of B, and then the probability of both. Okay? Probability of A here, identified tap water correctly. Okay, so we're looking at the identified tap water, and correctly means yes. Okay, so here there were 24 of those who drank bottled water, and then 36 who didn't. Okay, but the total here is what we really want to look at, is the 60. Okay, so we've got 60 over 100, or 0.6. Same thing for probability of B. We want to look at all the people who drink bottled water. Okay, so that's over here. Drink bottled water, we've got 30 in the yes, and no is 70. But again, we only want to take care of the ones who actually drink, so we want the yes row here. So our total is 30, and that's 0.3. Now, if we knew these were independent, we could just multiply those together to get to the intersection. Okay, but that's what we're trying to test here. Okay, so using our table, we're finding the overlap of A, which was identified tap water correctly, and B, which drinks bottled water. Okay, so identified tap water is yes here, and drinks bottled water is here. They overlap at that 24. So 24 out of 100. Okay. So looking at these, okay, hopefully you can tell directly 0.6 times 0.3 is not equal to 0.24. Okay, but we're going to show that over here. Okay, remember our proof. We're going to look at how, and I think we actually write the other one first, so let me stay consistent here, how the intersection compares to the product of the other two. As long as you know how to read this chart, okay, this is actually easier than some of those other problems that we've been dealing with where we had to come up with the intersection ourselves. Okay, so that's the difficult part, is being able to find that overlap. Here it was 0.24 as a probability, and we're comparing that to 0.6 times 0.3, and we know that 0.24 is not equal to 0.18. So we would say that A and B here are dependent. If we think about that for a little bit, it should make sense, okay? If you are able to identify tap water correctly, that probably increases the likelihood of you being a person who drinks bottled water. Okay, if you're drinking tap water all the time, okay, you may not be able to tell the difference between bottled water or tap water. Okay, so not always obvious to think about, which is why we do the math for it. Okay. This is another independent-dependent one. Okay, we're supposed to determine which of the pairs are independent and which one would not be independent. Okay, so the first step is getting a heart, getting a jack. Okay, so you're getting a heart and getting a jack. We're going to find the probability of A, probability of B. Okay, getting a heart, 1 out of 4. Okay, now here, it's saying drawing a card at random from a standard deck, and it really doesn't say whether we are replacing these or not. Okay, so it's really important that that's specified. So here, drawing a card at random, we're only looking at one card. Okay, so we're drawing a card. We want to know if we get a heart, does that make it more or less likely that we get a jack? Okay, so we're talking about the same card here, not two separate cards, if that makes sense. Okay, so we're not assuming that we're rolling, we're not assuming that we're drawing two separate cards. Okay, we're just looking at when we draw a single card, would getting a heart make it more or less likely to get a jack? Okay, so heart, there are 13 out of 52. Jack, if we think about drawing one card, okay, drawing a jack, there are 4 different jacks, or 1 out of 13. And we want to know if those are independent or not. Okay, so let's look at the product, or the intersection, excuse me. So A union B, okay, with the intersection here, we just want to think about whether it's possible to get a heart and a jack at the same time. And if so, how many of those happen in a deck? Because this in for intersection, okay, means where they overlap or happen at the same time. Okay, there is a heart of jacks in the deck of cards, but there is only 1. So 1 out of 52. And now we're going to compare that to those 2 separate numbers that we just got. Okay, so here, 1 out of 52. How does that compare to 1/4 times 1/13? And they're equal. So we would say that these ones, okay, are independent. And why that's the case here is because if we think about getting a heart, that doesn't make it more or less likely to have a jack, because there are the same number of jacks of hearts as there are jacks of other suits. Alright? Looking at B, getting a heart and getting a red card. Okay? I want you to pause the video and go think about what those 2 probabilities would be for this one. Okay, we can talk about the intersection together because usually that's a little bit more tricky, but pause and get those 2 separate ones done for me. Okay. Getting a heart, again, is 1/4. Getting a red card is not 1/4. If we think about the number of suits that are red, okay, it's both hearts and diamonds, so it's 2 out of 4. Okay, if we think about the total number of cards, it's 26 out of 52. Either way, we're reducing, to 1/2. All right. But then if we think about the intersection, okay, so A and B, we want to think about all of the hearts that are red cards. Okay, so what is all hearts and red cards? Okay, so suppose we're to list out all of the hearts. They would be the 2 through 10, okay, and then the Jack, Queen, King, Ace. Well, of those hearts that are there, all of them are red cards, okay, so all 13 out of 52, or 1 out of 4. Okay, basically it's we're looking at this probability and seeing which of those happen. Well, all of those original 13 will happen. Okay, so it's 1/4 there. And if you need to list it out, that's important to do, especially for those intersections. It's sometimes difficult to think about. Okay, so then we've got to look at our intersection compared to our product and see if they're equal. So I ended up with 1/4 for this. I want to compare it to 1/4 times 1/2. Okay, they're not equal. And that makes these dependent events. Okay, because again, if we're thinking about independent or dependent, dependent just means that the first thing would change the probability of the second thing happening. Okay, if I get a heart, the probability of me getting a red card is 100%. Okay, because if I have a heart, it is red. Okay, that changes the original probability of red being 1/2. Okay, so that's what we're thinking about. Would the probability of the first one change what happens with the second one? Make it more likely or less likely? Okay, independent means it wouldn't change. So I want you to pause the video and take care of number 6, or C, on number 6 here. For this one, getting a 7 and getting a heart. If I draw a 7, I'm still just as likely to get a heart, kind of like this first one up here, the order there. There are just as many 7 of hearts. Let's look at the actual probabilities, because again, thinking this through is not always clear, whereas the math is. So probability of getting a 7, I think it was, okay, there are 4 7s in the deck. So it's 1 out of 13. I'm just going to use 7 instead of A. Okay, so 1 out of 13. Then the probability of getting, just want to double check it is a heart, yes. Okay, of a heart is 1 and 4. And then the probability of 7 of hearts, which would be the intersection, there's only 1 of those in the deck out of 52. And then you'll notice the product is equal here. 1 over 52 is equal to the probability of the 2 separate ones. Okay, this particular problem, it didn't ask you to prove it. It just asked you, show me, are they independent or not, or what do you think they are? So if you're someone who can think through these problems confidently, and I don't say prove or show mathematically whether they're independent or dependent, you can just say which one they are. Okay, but because some of them are difficult to determine, that's why I'm showing you the math on this. Alright, next up, we're looking about number 7 here. It says about 42% people have type O blood. Suppose you select 2 people at random and check whether they have type O blood. So this is kind of like the first problem in terms of what's going on. Okay, we have 2 outcomes. Okay, because you're either going to have type O blood or you won't. Okay, we're not going to list the other types of blood that you can have because it didn't give us probabilities for those. Okay, we just know that not O, okay, is going to be the complement of this, 58%. And that's just a combination of all the other blood types, okay? So the sample space wants to talk about 2 people together. Okay, so we could have those 2 people both having O. Okay, we could have them both having not O, or we can have a mixture. Okay, we could have not O and then O. We could have O, then not O. And that's all of our options, because remember, if we have 2 people, and they each have 2 outcomes, 2 times 2 gives me 4 possible outcomes. So which of the one is most likely? Okay, this has 2 O's, this has 2 not O's, this has 1 of each, this has 1 of each. So which of the ones is most likely is to have 1 O. Least likely is both O or both not O. Okay. Now it says, what is the probability that both people have type O blood? Okay. So type O, we're talking about this, and we can't say it's 1 out of 4. Okay, because remember, we were told that these outcomes weren't equally likely, so we can't calculate it just using the sample space. We have to use those probabilities there. Okay, so we're going to say that probability of O is the probability of O, 0.42, and the second one has to have that as well, 0.42. Alright, so if we take that and square it, we've got the probability of both having type O as 0.1764. Now it says, what assumption are you making when we calculate this? What makes it okay for us to multiply these 2 together and do nothing else? Okay. Remember, this is saying, okay, I said out loud, this is O and O. we can say that we multiply these together, just the probability of O times the probability of O, when the events are independent. So we're saying that this first person's blood type wouldn't affect the probability of the second person's blood type being O. And hopefully that makes sense to you, because one person's blood type is not going to affect the next person's blood type as long as they're not related. Okay, so we're assuming the events are independent here. Okay, it says, how would A through C be affected if the two people were selected from the same family instead of at random? Okay, so here, A, the sample space, okay, wouldn't change. You still have these outcomes possible, okay? But if we think about outcomes being most likely or least likely, it's really going to be dependent on that percentage, because that percentage, instead of all people having type O, we're going to have way more likely those second person, or that second person, if they're in the same family, having the same type as the first person. Okay, so the probability as the first person would change. These are not independent. Independent events. Alright. Last couple here, it says Jill computes the probability that she got heads and at least, she got heads at least once in 2 flips of a fair coin. Okay, so at least once. And here's how she did it. She took probability of heads on the first one and probability of heads on the second one, because at least one means the first or the second flip, okay, or means add, and she got 1. So I want you to pause the video and tell me if you agree with Jill. If so, tell me why. And if not, explain why not, and then give what you think the probability should be instead. Okay? Alright, for this one, hopefully you said no, we don't agree. Okay, because you can use this OR if you subtract off the intersection. Okay, if we think about this sample space, we could get heads, heads. Okay, we could get tails, tails, or we could get heads, tails, tails, heads. So here, at least once, remember this is the complement of none. Oops. So at least one heads, here's the one that works, here's the one that works, here's the one that works, but we could say 1 minus none. Okay, or here, if we take the probability of heads on the first flip, there's 1, 2, 1/2, 2 out of 4, plus probability of heads on the second. So heads on the second, there's 1, there's 2, so 2 out of 4 is 1/2, but we have to subtract off where they both happened. Okay, this is the intersection at 1 out of 4. Okay, so 2 ways to do this. Okay, she forgot about the intersection. And counted an outcome twice. The probability of at least one heads is really 3/4. Okay. Last one here, we're going to do some vocab and quickly answer these questions using our definitions of our vocab. Okay, it says, decide which, if any, of the terms below apply to the events A and B given in each example. So mutually exclusive, remembers no overlap, so no intersection. Complementary is no intersection, but also probability equals 1. Let me fix that so it looks a little better there. Independent is our definition, the product equals the intersection. And B would mean none of those things are true. Okay? So we're adding in the independent option from some of these things that you've done before. Okay, so let's look at the first one. Let's first decide on this one about the intersection or not. Okay, so mutually exclusive can't have an intersection, so we want to take care of those first. They're easiest to see. Okay, well, on this first one, they don't give you what the intersection is. Okay, they give you the union instead, and that's where we're going to use our formula for union on the front side of your note card. Okay, it says that the union of A and B is equal to the sum of the two separate ones. But remember, we have to subtract off an intersection if there is one. So, similarly, we could say that the intersection, if we move some stuff around by adding that over and subtracting that, is equal to the two separate ones minus the union. Right, so on this one, let's find the intersection, doing what we just talked about. Okay, we're going to take the two separate ones, add them together, and that's 0.6. And we'll subtract off the union, 0.6, and we get 0. So far, I know they are mutually exclusive. Right. Now, I want to decide if they're complementary as well. Okay, well, complementary has to mean that the union equals 1. Okay, the probability of the two things together is 1. Here it's not, so it can't be B. Now let's look at if they're independent. Do the two separate ones, when we multiply them together, give us that intersection of 0? Okay, unless one of these is 0, that's not going to happen. Okay, so first up, just A. Second one here. Again, let's find the intersection first. Okay, we're going to add up the two separate ones. That's 0.7. Subtract off the union, 0.6, to get an intersection of 0.1. These ones do not have an intersection of 0, so they cannot be A or B, but we can check for independence. Okay, so we want to see if multiplying A and B together give us this. Okay, so 0.2 times 0.5 is 0.10. That's the same thing as that, so these ones are independent. Okay, I want you to pause the video and try the next two for me. Alright, so here, when we add those up, we get to 1, which is the union. That implies the intersection is nothing. Okay, both mutually exclusive and complementary here, since they add up to 1 together. Then independent is not happening because when we multiply those together, we don't get 0. Last up, it gives us the intersection already. Okay, now because this intersection isn't 0, we can't have A or B happen. Those are gone. We can only test for independence. And when you multiply those two together, you get the third one. Okay, so that's good news. They are independent. You didn't have to find the union here because you were told that the intersection was not 0. Okay, but it doesn't hurt to find it if you want to. All right. Hopefully this cleared up some of your questions or struggles with probability stuff that we've covered so far. But if you do have any trouble completing the homework or have any questions on what we did today, please feel free to come see me.